So we've been looking at each individual instructions, and in this week, this is usually the holiday shortened week, we would only look at one step above that, which is to code some reasonably sized program. And at the very early stage of the computing history, it's binary. Okay? We have to code in binary. And perhaps a little bit better, it would be this thing called assembly language. And we'll see about that. We are by now familiar with all the instructions, the hardware, how the each instruction controls the various gate of the hardware to serve a purpose. So now what we wanted to do is to code, let's say, one program. And we had this. Usually we practice that in class. If you haven't done that, you really should go ahead and try that. You have all these instructions. Okay? They're somewhat broken down already. Excuse the alignment of the vertical lines. So you have the opcode. This is, by the way, higher order bit on the left, lower order bit, least significant bit on the right, exactly the same format as we saw here. So you can match 1110 is which instruction. You can look at the table and see, oh, that is an LEA instruction. So go through this exercise and we will see what the code is trying to do bottom up. We're looking at binary code and we want to analyze what it does. So that's a load effective address instruction into register R1 with a very long offset. In fact, this offset is fairly easy to understand. It's almost 1 followed by a whole bunch of 0. So that's easy to calculate. The next instruction is 0101. And again, you can look at this and say, oh, it's AND. It's one of the AND. It's either with an immediate input or with a regular register input. And in this case, that's AND, destination register R3, source register, source register R3 with a 1 in it. This means the second source is an immediate value and it's 0. Okay, you can immediately see what it does. It's an AND instruction with value 0. So it doesn't produce any useful, original, it erases any value. It's going to produce a 0, and so on and so forth. You can go through all these instructions, and that's the exercise we have. We're just going to skip through this step because it's kind of straightforward, perhaps a little bit painful, but rather straightforward. Now, what we're showing here is no longer instruction format. It's kind of what it does, right? The destination register is 3. Okay, it really doesn't matter what the source register is because you're ending it with a 0. So this is really just initializing register 0. And similarly, that next thing was to initialize register 2 because it's the same type of instruction with a different offset. The next one is an add. That's right here. The one following that is a branch. This one, let's explain a little bit. The flag is 010, and according to this, that's the Z bit. This means if the 0 instruction or 0 bit is set, we're going to branch. Otherwise, we're not going to branch. So once we've laid down all these things, we can see that these are initialization. We set R1 to some value. Okay, what is it? It's adding an offset. And the reason the offset is 1 followed by zeros, this is in hexadecimal, is because, again, we said this very early on, the first thing you do is to send the PC, the hardware. What it does is it sends the PC to the memory address register, okay, for loading. And then immediately PC becomes PC plus 1. So by the time you actually execute this instruction, the PC is already incremented. Okay, so we have to add one more 1 to this offset, and that turns out to be hexadecimal 100, which is decimal 256. You add that to the PC, that's your effective address. But load effective address is not a load instruction. What you're doing is you put PC plus that offset into the destination register. So that's what it is doing. It's initializing R1 to some value. So after this, R1 is going to be 3100 hexadecimal value. R2, 3 are going to be 0. R2 is then again added by an immediate value of 12, 1100. And what do you think the value is? Well, R2 is set to 0 here. So the value is 12. Is it 0? No, it's positive. So the branch is not going to happen. This branch, at least for the first time, is not going to happen. And we're going to keep on executing until the last branch. So leave the body, this body of code or of instructions aside for just a moment. Let's look at the branch, the last instruction branch. And we'll come back to these 4 instructions. So this is, again, a branch with all 3 flag bits set. Now, what does that mean? It's an unconditional branch. It says if the flag N, Z, P, any of them is set, we're going to branch. So what are the NZP? The value from the previous calculation is either 0, negative, or positive. That's all the time. Okay? It has to be one of them. So this branch is always happening, and we can calculate this. Okay, this is a negative value. It's a 9-bit negative value. We want to know, let's say, what the exact value is. What do? You flip all the bits. This is again 2's complement. Okay, you flip all the bit and you add 1. So if you flip all the bit, it's going to be 101, and you add 1 to that, it's going to be 110, which is 6. Okay, so but it's branch with an offset of -6. But the offset is from what? Is always from PC plus 1. So the PC is already 3010, sorry, is 0A. By the time we execute the branch and we subtract 6 from it, and if you do the math, that's going to be 3004, which is this instruction over here. Okay? So what does that do? We're branching back. And this time, we branch back after which instruction? After what calculation? What's the previous calculation? It's R2 equals R2 minus 1. So now you should see that this is a loop. We start to set R2 to 12. That's what C is. We execute the body of the loop. And at the end, we decrement R2. Okay, and then we unconditionally go back to do the test. Yes, it's a little weird, but you can do that. And the test is to see if it reaches 0. And the first time it's not going to reach 0. Next time it's not going to reach 0, but it keep on decrementing. So this loop is going to loop iterate for how many times? It's going to iterate for 13 times, because I start with C, I do this. Okay. Oh, sorry, 12 times, because I do this right in front. So the first iteration, I start with C, but at the end of the loop, it's already C minus 1, which is 11. So you start from 11, you go to 0, and you finish. When you finish, you branch to 3008, which is right outside the body of the loop. Okay, so now we already had a higher level view of this piece of code, which is, it's a loop. Now let's look at the loop body. That's the interesting thing. This is a load instruction. Okay, 0110. That's a load with relative. So you take the base register, in this case 001. You add some offset to that. Very easy, in this case just 0. And we take the memory value out of it and put it into register R4. So that's what we're saying over here. We go to memory register, we go to a memory location indicated by the value of R1. And what's R1? We calculated there before. It was 3100. It's there. We go to that location, never mind what exactly it is. We load the value out of it, we put it into R4. Then we add this R4 to R3 So this is accumulation. Next iteration, the R3 is going to be higher, and we're going to add a new R4 to it. So we're really just adding a whole bunch of R4s, each one loaded from a memory location, and each time the memory location is bumped up by 1. So what happens is there is a location 3100, there's a value to it. And then 3101, there's another value to it, and so on for 12 locations. So the last one would be 010B. Okay. We added all those 12 numbers together. And at the end, when we're done, we're branching off to this location. The real interesting value out of this is R4. R3. R4 is simply the value that you put temporarily. You load from memory, you put it in R4. But then the interesting thing happens here. So what this code does is to add an array or a sequence or a collection of numbers residing in consecutive memory locations. It's adding up a vector, if you wish. So that's what this piece of code is. And if you want to write that in higher level language, it's much shorter than that. Okay, so again, at the dawn of the computing age, programming wasn't done with any comfort that you imagine today. In the ENIAC, we have to actually hardwire things. And later on, things gets easier. You can scan things, so that's your input mechanism. So this gets loaded into computer, but still mechanical. Later on, you have tapes, so you can store the program and retrieve from it. And this is a hard drive that is 5 megabyte. Okay, it's not terabyte, not gigabyte. It's 5 megabyte. Look at the size of this thing. So if you had to hardwire code, it's very difficult. And one of the important concepts IBM invented was the binary compatibility. So they had a family of computers called IBM 360. You can build a bigger one, you can build a smaller one. One has more memory, the other has perhaps faster CPU. You can buy all of them, but they all share the same instruction set, which is what you're seeing over here. This is an example. Why we're calling this computer LC3? The authors of the textbook went through different iteration of it. Do they change the instruction set? Not a lot, but they can. But usually it's adding rather than subtracting an instruction. Why? Because if you designed an instruction to say, well, load is going to do this. This instruction 0010 is going to do this. Later on, if you decide, I'm going to change that, then the old code will change its meaning. Because the instruction, if the code uses this instruction, it will mean a different thing back then as opposed to now. But if you're only adding instruction, let's say the example over here, I have a reserved instruction. I didn't define it. In the early stages, I give this ISA specification to the programmer. They're not going to use this instruction because it does nothing. And later on, or it's reserved, it's really, I'm not guaranteeing that it's doing nothing. Okay, I'm saying this is being reserved. If you put it in, you're putting in something at your own risk. The program may not run and it may crash, and that's your problem. We already told you so. So later on, I can use this reserve slot to add a new instruction, and this happens all the time. But by and large, it's binary compatible, meaning the old code can still run on a new machine. The old code obviously is not going to use the new instructions that we just put in a new generation of computers, but it still will work, okay, as what's been done in the past. So once you have that, you can ship customer storage device that contains the binary, okay, and then they will be able to run on different machines, and they can keep that binary and load onto a newer machine, so the code will still do the same work, only perhaps faster. So this has been a modus operandi for the industry for a long time. And because binary writing, as we've seen over here, is incredibly difficult, okay? Not intuitive at all. So this is terrible. But this is less so. We can look at this and make some sense. And that's the next level, and that's assembly programming. We're gonna try to not do the last stage of translating something that is semi-human readable to something that's just completely alien to us. Okay, that is the level that we're going to deal with, and that's called assembly. It's just the name. We're not picking up any particular assembly programming. We're not teaching you x86 assembly. We're not teaching you ARMS assembly. We're taking a look at LC3 sort of to see assembly level programming, okay? Not any specific machines code. So it's not a programming language as Python is, okay? Very few people would actually code in a particular machine's assembly code. Doesn't happen that often. It's useful for reverse engineering, for debugging or whatever, but generally, this is one way of looking at the machine. We got a hierarchy of different interfaces. We have a problem that we want to solve, but at the end of the day, the computers are made out of some device, CMOS transistors, okay? And these transistors can make you interesting circuits, NOR gates, NAND gates, register, multiplexer. We've gone through all of them, and we put them together into a microarchitecture, the LC3. But that microarchitecture presents a stable interface called the instruction set architecture, meaning next time we can use something else to implement the same LC3. It could be we found a better circuit. All of a sudden, we don't need so many gates, so many transistors to build what we want to build. Maybe we had a more powerful microarchitecture. We're trying to execute 3 instructions in one cycle simultaneously. Or maybe we found a new kind of device that is based on carbon nanotube rather than silicon semiconductor transistors, okay? But the instruction set remains the same. So the code that people build on top of that superstructure is stable. We don't have to rewrite every single thing, okay? So the problem is an abstract problem. Let's say we have, I don't know, a map of 200 cities, and you want to tour over them, the traveling salesman problem. You want to go through all of them, selling your product. This may be a book tour or whatever. And you want to find the best route to save you time and money. How do you do that? And you have a whole bunch of information. You have, let's say, between any pair of city, the travel cost or distance, whatever you want. And you want to go through all 200 cities and minimize that. There are algorithms for that. Someone invented an algorithm one. Let me tell you the simplest algorithm, right? Simplest conceptually. Let's enumerate all possibilities. If you have 200 cities, then that will give you 200 factorial number of possible ways of going through it. Okay, you can, for any path, I guess you can go back and forth. You can go from city 1 to 200, or start from 200 back to 1, they're substantially similar, it's just reverse. So okay, maybe this is not how many you need to travel, you need to search half of it. But still, that's an incredibly large number. Okay, so there are much better algorithms to go through that. And you find one such algorithm. By algorithm, we mean it's substrate neutral. It doesn't matter what you're implementing it. You could do this at the back of an envelope, albeit a very large envelope, by hand. You say, this is what I'm going to do. I'm going to calculate this, and if this is greater than that, we're going to do this, and so on. But you can also write it in code. And that's when you pick up a language. It could be Python, it could be C. You use the tool, you compile it down to instructions. Now this is finally all tied together, and you see the product. This is the product. Okay? At the end of the day, no matter what you choose, this is what the machine sees. Except we don't want to code this by hand. So let's see how we build this superstructure. Let's see how we write something that does a very simple thing, but in more readable format. So what do? We're going to code in this format. Okay? An opcode, destination register, source register, and so on. Okay? So instead of saying add is 0001, we're just going to say add. And it's very easy for another program that we're going to write to change this into that code, okay? Into that binary that the computer is going to recognize. So the exercise we did is, okay, let's add a number n times. And let's see, how do we express that? And you will find out that there are some things that is beyond the capability of individual instructions. You can't do certain things. It's not an instruction. It's not that I don't have the instruction, but I need to do certain initialization, and I don't want to do that by hand. So you see that LC3's assembly already provided some things to simplify your life. Okay, so if you took the time to write this piece of code, to say I have two numbers and I'm adding and multiplying them, essentially. So let's say one is 4, the other is 7. I'm adding 4 7 times, which is the same as multiplying 4 by 7. How do I do that? And what are the problems you encounter? Some of the problem is, okay, how do I initialize memory? Suppose I get my source from memory. So my code is not hardwired to multiply 4 by 7, because then I know the answer. I don't need to write a piece of code. So the code will look in LC3 something like this. Okay, that's very easy. We're going to load into R1 one of the multiplicand. We're going to load into R2 the other. Okay? And we're just going to add. Okay? We're going to add the number in R2 so many times. How many times? R1 times. Okay? And so we start from 0. We know how to do that. We set a register to 0 by doing something like this, ending the register with value 0. And then we start to add R2 into R3, and then keep on repeating. So we're going to go back, do this again, go back, do this again. Meanwhile, we're subtracting R1 because R1 tells us how many times we want to add. And once it becomes 0, we're no longer going to do a loop. So the branch that we're going to use is branch if still positive. So by the time it's 0, we will go out and then we're done. For now, let's just worry about that. So we'll stop there. We're not going to print it out or anything like that. Okay, so what did we need in order to make our life easier? Well, first of all, we need some value. We need some number. Where do we put the numbers? In memory. How do you do that? Here's two ways. Okay, one says, okay, I have some memory location. It's not an instruction. I just want to put the value 6 in that memory location. That's fine. You can do that. You use fill. Now this color is it's not an instruction. It's what's called a assembly directive. We're telling the assembler, we're telling the code that generates the binary, this is what I want to do. You generate the binary. You take this instruction. Well, eventually that converts into, I don't know, the load is 01010 or something like that. You convert it into a 16-bit value, right? One by one. But here, just put the value 6 in there. That's what we want to do. Okay? So that's one way of initializing memory. Another way is over here. Okay, where you say, I want a block of memory set aside for me. Okay? In this case, I don't care the value, which means the assembler is well within its right to simply give you 0 to fill everything. So what that means, what this directive means, is to create a block of words. How many words? In this case, I just want 1. Okay? You can put 3, then that would be 3 spaces. So now, when I load the program, what happens? All this binary is copied into memory. At what location? Well, it's going to be some location, and you can specify that with this compiler directive or assembly directive, sometimes called pseudo instruction. Okay, that's to say, put it there. Originate from x3050. And at the end, you say, okay, stop. Nothing goes beyond that. One last thing that we need some help is labels. We can certainly do the calculation. Remember, this is going to be quite tricky. We say, okay, at here, we want to go back 0, 1, 2. But since the PC plus 1 thing, it really should be 0, 1, 2, 3. So we need an offset of -3 in our code. But I don't want to do that. It's error prone, and if I put in any instruction, I have to recalculate all my card. That's just pain in the neck. So what do? I introduce the notion of labels, which are these blue things that you see. Okay, I put a label in there, and I simply say, go branch there. You tell me. You go figure out, you being the assembler, what the offset is. So we have 3 such labels, and then we're done. Now, this is all, you have things like comments that's given to you, but this is all the code that you're going to write. Now, the question may be, how does the compiler or the assembly code, the assembler, know how to generate this? Well, it's actually not that difficult. It goes something like this. Here's a bunch of cartoons to show you, right? I am now pretending to be the compiler. What am I doing? I'm scanning the file. What is this? This is a piece of text file. Okay, this takes a lot of space. There's, maybe let's just pretend these are all spaces. Each one is a character. It's a very long text file. So I'm reading all of that. So okay, space means nothing. Okay, but the first time I see dot, I know, that's something for me. I'm going to read that. And what you find out is, that's telling me where to put this code. Got you. Now, next time I read another instruction, what do I see? I see a label. What is SIX? Have I ever seen it? No, right? So what do? I have my little book over here, okay? My symbol translation table, if you wish. I'll say there's going to be a symbol called SIX. I don't know what it is now. Let's leave it empty. I look at the next instruction. Another symbol called NUMBER. I don't know what it is either. There's a printout issue. This is really, it's over here. This -1 should be over there. I don't know why it shows up incorrectly on the iPad. But okay, it's not a symbol. The hashtag 0 is not a symbol. It's just immediate. So we keep going, and now we see, again, this time we see the label first, which we will know the address. Why? Because we know that it starts at 3050, so this is 50. Next instruction is going to be 51, next instruction will be 52, and this instruction is going to be 53. And that's why we figured out the address is this. So if we keep going, eventually we will see these symbols. And if we don't, we'll complain. We'll say, label undefined. This is no different from when you have a programming language, when you have a Python code, you say x equal fox plus 3, and you've never defined fox. Okay? Unknown. You use the label that we don't know. So if I scan this once, I will, at the end of the day, know exactly what those labels are. And I can go back and scan this one more time. This time, knowing the address, I can generate the offset for branch, I can generate the offset for load, and everything is going to be done. And that's how this piece of code can be translated into binary. And next week, we're going to see how the operating system is actually using this same mechanism to write and allow the hardware to interact with the software, to support what the software needs to do.